All right. So we are continuing our discussion in this section on experimental design and what goes into making a really good experiment. On our slides in this section, you guys are going to see a lot more typing than I usually like to do on these slides right here. This is more just for later for you guys to have something to look back at and read in your notes, but I'm going to try to summarize each of these things as we're going through them. So we are still in the context of our caffeine experiments from last time. So if you guys can think again, the idea was I was going to see if having caffeine makes a difference in your pulse rates. And then we were talking about different things I was doing or needed to do to make sure my results were worthy of actually being analyzed, to make sure my design was good. So last time we only talked about one aspect of experimental design. And that was the idea of having a comparison. You have to have at least two groups. If you don't have two separate groups to compare, you can't say whether the results that you're seeing are because of the variable of interest or because of some other factor. My example last time was if I give everybody caffeine, I wait and I measure. Maybe my awesome stats lecture in the meantime is what increases that pulse rate. So I need to make sure that I have at least two groups that both experience the same thing. Two groups that were experiencing all the same things except for that one thing that matters, which is caffeine. So I'd have a group that got caffeine and I'd have a group that did not, that all heard the same lecture. So if my lecture was really what was going on, I would see both groups having a higher rate. And if there's still a difference, it would be because of the caffeine, not because of that factor that was the same between them. But even if I have two groups, if I'm not careful about how those two groups are made up, I could still run into issues. So I need to make sure that not only do I have two groups, but that those two groups are evenly balanced. We have to do what is called random assignments. So we randomly assign subjects to treatments to create groups that are roughly equivalent at the beginning of the experiment. Underline and put a star by that line, roughly equivalent groups. So let me talk about what this means. Let's say I was going to do the caffeine study and I realized, okay, yeah, gotta have two groups, gotta have a comparison. But then I just let people self-assign to their own groups. It seems plausible to me that if I just let you guys assign to your own groups, you probably wander over to the group, whichever group you end up being in. Maybe you wouldn't even know what group it is, A or B, but like you would probably migrate with your friend group to whichever station you're going to go to. So people who are friends in the same group would probably go over to the same treatments. Well, let's say you and your friend group are just going to get coffee every single day before school. You're getting a triple, espresso, mocha, whatever, and you're just really, really tolerant to caffeine. And all of your friends go there together, so you guys are all pretty tolerant to caffeine. So you're all in the same group right now, and you probably would experience almost nothing due to the fact that you're used to the caffeine. So what could that do to my results? If you guys were in the caffeine group, I would see that and be like, wow, caffeine actually didn't make a difference at all because you're so used to it. Or if you were in the non-caffeine group, then I would be like really confused with what's going on. Or on the reverse, let's say you never have caffeine, your friends are all anti-caffeine, and you guys get the caffeine. I'm going to be like, what is going on here? This caffeine makes such a big difference. We could talk about athleticism, people who are physically fit going into the same group, et cetera, et cetera. If I let you choose your own groups, that concept of confounding comes back. I won't know if I let you choose your own groups if it's your caffeine status or what, blah, 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 or athleticism or blah, 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 or whatever. So you need to make sure that when you make your groups, you're splitting it up. So you have people who have caffeine tolerance in both groups. So you have people who are athletes in both groups. And the only way to do this, just like we talked about last section, you can't trust yourself as an experimenter to break that up. You have to trust a random process. The only way to be sure that it wasn't because of this or this or this or this that are confounded with your variable is to break your people up randomly. Why does that matter? If they were randomly assigned, you should get about the same number of athletes, the same number of caffeine people in each group. Okay? Is it possible that you get a few more in one than in the other? Well, yeah, it is. It could work out that way. But if you have enough data, you're going to be okay. And basically, what random assignment does is it stops people from being like, oh, did you consider this? Or, oh, what about this? Oh, did you think about what people are eating for breakfast? And you could be like, hey, I randomly assign treatments. So, random assignment is like a kind of just quick boom. Hey, I did random assignments. I'm good. So let's move on to our next principle of experimental design. Oh, actually, wait, I forgot I did this first. So let's talk about designing an experiment here and the concept of completely randomized design. When you have a completely randomized design in your experiment, it's basically what you probably think of, or what I just described on my last slide, where I break you guys up into groups randomly. If I asked you to describe a good experiment, there's a pretty strong chance it would be this kind. Kind of a different type of experiment that we will talk about later in this chapter is blocked experimental design, or randomized block design, and we'll get to that. But this just generalized randomized design is when your experimental units are assigned treatment entirely by chance. And you will be asked sometimes on the AP test to describe a randomized design either by like a list or by making a diagram. And I prefer writing down like a bulleted list, like boom, 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 this is what I would do. But I'm actually going to do it via diagram right here. So at the time I'm making this video, I don't know who all is I don't know the number of kids in my class yet. So I'm going to say there are 18 of you guys who are in my hypothetical caffeine study. I start out with my 18 students. And the first thing I need to do with my 18 kids is I need to break you guys up into the treatment groups. So I need to figure out somehow how to do random assignments. That could happen a lot of ways. I could give you guys each a number from 1 to 18, and I could randomly pick you 9 numbers, no repeats. Those 9 numbers, those people go in the first treatment group, then the remaining 9 go in the next. I could instead pick index cards or papers, put your names on the papers, put them in a hat, shake them up, pull out 9. And there's nothing that says you have to do the same amount of people in each group, but unless there's a compelling reason to do otherwise, that's what I'm going to do right here. So I'm going to use some sort of random assignment, and I'm going to break you guys up into 2 groups of 9. So we're going to have group 1, and the variable n is one we use a lot. N is sample size. So I'd have 9 people in this group right here. So it's the size of my group. And I'd have group 2, which would also have 9 people in it. Each of those groups is then going to get their treatment. So the treatment in this case, it doesn't really matter which group is which. Say treatment 1 is going to be the caffeine group. So I give you guys caffeine. And then treatment 2, you guys are not going to get caffeine. We're going to talk later in the slides about how giving like a caffeine-free soda is better than giving no soda at all. And we'll talk about that later. But for right now, I'm just going to write down no caffeine and leave it at that. And after we actually get our data, so we do the caffeine, we do the no caffeine, the part people always forget when describing an experiment is that you need to make sure you actually compare the results between the 2 groups. So measure pulses, measure your pulse change, and then compare your 2 groups. The whole point of doing the experiment is to pit this group against this group to see if there's actually a difference in pulse rate. So once you collect your data, you need to make sure you actually compare the 2 groups to see if there is a difference. All right, so that is an example of an experimental diagram right there. You could have done that same thing by making like a little list of things to do, and I like that better, but now you've at least seen one of those diagrams. Let's move on to our next principle of experimental design, which is a concept called replication. So replication is what I want you guys to write on this blank up here on the top. And replication, in a nutshell, means making sure you have enough data. You got to make sure you have enough data when you do a study. Let's say I have 4 people. So I only have 4 people that I'm going to do my experiment on. If I only have 4 people and I randomly break them up into 2 and 2, there are so few people that it's totally plausible that these 2 are athletes and these 2 are not. These 2 like coffee, have it all the time. These 2 never have caffeine. When your groups are too small, Random assignments doesn't get to kick in and do its job. You got to have lots of people. And if you have lots, then when you break it up, the chances of one group being drastically different than the other, very, very minimal. But when your groups are too small, you could have a fluky thing where this group is actually different in some way than this group over here. So having too little data is a huge issue in experiments. And honestly, 18 people in a class really probably isn't enough for a good study. No scientist is going to publish my study because we just don't have the data on hand to make it work. In addition to not having enough data points, the other thing going on with replication is it needs to be possible to repeat the process, not only in like your one trial, but to take the whole thing and to do it again. Those of you who are involved in science research, you've probably heard the concept of replicating results in an experiment. Basically, if I'm a scientist and I do some crazy study and I find just the most amazing results, if other researchers can't repeat my process and produce the same results, my results are worthless. Okay? You hear about like I feel like in the news all the time, there are studies about the next new wonder drug and this awesome thing that's going to solve all these problems. And you hear about it in the news, but then it kind of goes away. It's something where the results worked the one time, but they couldn't be replicated reliably. So that's a problem that you need to be able to do it again and again for the results to actually be significant. So when we do have good replication, it can help us feel more confident applying the results of our experiment to a population. All right, so let's keep things moving and talk about our next principle of experimental design. And this is a huge wall of text right here. So you can pause me if you want to read through this or read through it afterwards, but do read it at some point right here. I'm going to give you guys kind of a summary, though, of this principle, which is called control. So if you could go ahead and write control on that top blank, I will now kind of break down what that means. Control is a really big concept, and it's not the same thing as having a control group. Control group is like a buzzword. Oh, you got to have a group that doesn't get anything at all. And then people just think that's what this is about. Control is a much bigger issue than just that. What it basically means is making sure everything is the same between your treatment groups, except for that one thing that you're actually testing. Okay? So let me give you several examples of that. And you guys can see on the slides right here, there are two primary benefits to control. One is that it prevents confounding, and one is that it reduces variability. So I'll talk about those two things separately. Let's start out with confounding for this first one right here. So still haven't gotten to why, but it's not a good idea for me to give one group caffeine and one group absolutely nothing. It's the placebo effect, which we'll talk about later on in these slides right here. So let's say I have these two groups, and I have the caffeine soda, and I've done this before actually. I've gone to Schnucks or whatever and bought some caffeine Pepsi, and then all I could find was diet decaf Pepsi. Decaffeinated soda is harder to find, and all they had in stock was diets. Well, then I've got caffeine regular Pepsi, and I've got diet caffeine free. Caffeine Pepsi has sugar in it. Diet does not, has like artificial sweeteners. So everybody who got caffeine also got sugar. Everybody who didn't get caffeine also got like fake sugar. So if I see a difference in my groups, it's confounded with sugar is confounded with caffeine. I can't break those two apart. And if I see a difference, I don't know if it was the sugar or if it was the caffeine that made that happen. So it's dangerous when you have studies to let more than one variable run wild, because if you do that, you can't say for sure which of the variables is actually responsible for that difference. Okay? So that is one factor you definitely need to consider. The other kind of thing going on with control, in addition to like confounding and having that going on, if you don't control for variables, you will have higher variability in your responses. So let's say I decide that I'm going to do my caffeine study, but I'm not going to specify how much caffeine you have. You guys just go wild. Take however much soda you want. You want to drink like this much? That's cool. You want to drink a whole 2 liter? Have at it. It's just up to you. You decide. Well, then, logically, the people who had more caffeine, if you drank a whole 2 liter during that time period, you're going to experience more of a change, presumably. If you drink your soda really fast, so instead of just amount of soda being the same, if you just chug your soda, I don't know, maybe that makes a difference and makes you feel the caffeine more than if you sip it gradually. Other things at play, if like certain cans of soda are at different temperatures, maybe the colder soda lowers your pulse or whatever. I'm recording this video summer of 2020, so I don't even know yet if I'm going to be seeing you guys in person for this lesson or if it's going to be like a virtual deal. If like some of you are at home doing this study and you've got music playing in the background and that's pumping you up and some of you don't, or somebody's yelling in your house, there are lots of different variables that I wouldn't be able to control for. And those variables changing will affect responses and just make my results more spread out than I want them to be. Okay, so this slide talks about that in a bunch of detail. So let me kind of explain a little more that second thing about reducing variability and why we want lower variability in our responses. So this dot plot on the next page has two hypothetical scenarios. This is focusing specifically on the amount of caffeine. So making sure that I keep the caffeine consistent for everybody. So in my first little dot plot right here, these people were given the same amount of caffeine, and these people were given the same amount of, like, let's just go with caffeine soda and then caffeine-free, same soda. Want to make sure they drink the same amount of soda, not more or less, depending if you have caffeine or not. Same temperature, same everything, same rate of drinking. Only difference is these guys got X amount of caffeine. You can see in the results of this study that these people over here have positive changes in their pulse. Now, when you talk about a change in the pulse, I'm assuming they took the after minus the before, although it didn't super specify right here, but that would seem logical to me. So if my pulse beats 40 times and however long I timed for afterwards, and it was 35 before, that means it changed by 5. So this is the difference of their pulse rates right here. These numbers for the caffeine group are mostly higher than these numbers right here for the no caffeine group. So I would look at this and be like, oh man, caffeine made a difference. That's what this would lead me to believe. So it seems like caffeine seems to make a difference. Okay, that's what I would think if I saw these results right here. Meanwhile, in the second scenario, this one, kids were allowed to choose their own amount of caffeine. So if you look at this right here, what you're going to see is more variability or spread in your results. Results are a lot more all over the place. This kid over here probably drank a 2 liter of soda, where this kid was probably sipping on just a little bit right there. So if caffeine actually makes a difference, you see a lot more spread in your results, okay? Spread in your results is not desirable. You don't want that if you can avoid it. And the reason for that is the first one, it was pretty clear that this group is bigger than this one. But in this second one, look at how many of these people experienced very similar results. These people and these people got about the same results right here. There are a few people on the high end and a few people on the low end right here. But if you have, like, basically that makes this data less relevant. Look at how many fewer data points we're looking at now, as opposed to everything as a whole. So if we do that, picture if like two of these people were not in the study anymore, all of a sudden you really can't tell that this group is better than this one. So when we look at dot plots like these, we don't want to see a lot of overlap. Not a lot of overlap means there's probably a difference. Lots of overlap between them means it's harder to see what's going on. So if I saw these results, I would be unsure of what was actually happening, okay? So you have to have control. Control allows you to lower variability in responses. If you don't control, you get increased variability, which makes things unclear. I have one more question on this scenario right here. Would students' weight be a confounding variable in this experiment? So what do I mean by that? Weight plausibly seems like it would make a difference in the change in your pulse rates. If you weigh more, the caffeine that you have, if everybody's getting the same amount of caffeine, that caffeine probably isn't going to have as big of an impact on you because you've got more mass for the caffeine to spread out across. When you weigh more in general, things have less of an effect. On the other side of things, if you don't weigh very much, that same amount of caffeine may hit harder for you and have more of an effect. So the question was, is caffeine a confounding variable? Now remember what it means to be a confounding variable. It means that you have these two factors that are tied together that you can't separate to say which variable is actually causing the change that you're seeing. So in this context, it would mean that weight and caffeine are tied together in a way that I can't tell which one made the difference. That's not what's going on in this study. I randomly assign people to treatment at the beginning. So if I randomly assign people to treatment, people who weigh more should be balanced between this group and this group. People who don't weigh as much, balanced between this group and this group. Random assignment is basically our way of ensuring that variables don't get linked like that and we can actually tell what's going on. So would weight be a confounding factor? No. Treatment was randomly assigned. So, I'm off the screen right there, sorry. Treatment was randomly assigned. So weight should be balanced. Should be balanced. I just can't write between groups. So if you randomly assign treatments, you avoid that possibility. You kind of sidestep the worry of, oh gosh, which of those variables was it? The group should be even, except for the caffeine, the thing you actually care about. So let's keep things moving on our slides right here. And the next thing we have to talk about is more text right here. I've already referenced one of these things, so I'll remind you guys again. When you do a survey, it's important that subjects in both groups are blind to what treatment they receive. And I'm going to put blind in like quotes right here. This doesn't mean like physically blind. The idea is that if I'm doing this caffeine study, I shouldn't know if I'm getting caffeine or not. If I know I'm getting caffeine, my pulse may actually start to raise just because I expect it should. Your mind can actually play tricks on you and cause real responses in your body just because you think something is supposed to happen. That's a very famous concept called the placebo effect. So if you are not blind to treatments, you run the risk of being fooled by the placebo effect. If somebody expects something to happen, it may actually happen even if it wasn't caused by the caffeine. You may have a higher pulse just because you think you're supposed to. That can happen with medications too, even with like crazy things. Like it can be very concrete things like anxiety, but also like, I don't know, some sort of illness that you have getting better faster. Your mind actually is very powerful. And just because you think you're getting treatments, it may actually cause like you to get better just because your mind convinces it to happen. So you want to make sure you don't know what treatment you're getting as a person involved in the experiments. Sometimes it also makes sense for the researcher to not know who gets the treatments. And in that case, it is called a double-blind study. So when the researcher doesn't know, somebody knows. If nobody knows what's going on, then how are you ever going to find out what treatment you got? It's like the results are lost to you. So there's somebody behind the scenes or it's recorded somewhere. But let's say I'm the researcher. Sometimes it may be beneficial for me not to know either. In the caffeine problem, it doesn't super matter if I know or if I don't what's going on because I can't have any sort of influence on the results. We're counting your pulse rates. But let's say instead I was measuring how relaxed or how calm you looked or how anxious you looked or something like that. If I knew what treatment you got, I may subconsciously be like, oh, they got the good treatment. So yeah, they do look more relaxed or ooh, they look more anxious. And my own biases could kind of cloud my judgment right there. So you want your study to be double blind, not all the time because it's not always helpful, but it's useful when the researcher must be subjective. So when the researcher must be subjective, you want to make sure they're blind so they can't have their own biases come into play. All right, a couple more disclaimers here. Not every single experiment needs to have a control group that gets no treatment, needs to have a placebo, as long as you have a comparison. So people will mistakenly say, oh, not a good experiment, there was no control group or there was no placebo. Basically, let me give you a few examples of why that may be. The most important thing is that you have a comparison. You have to have multiple groups, but you don't always have to have a group that gets no treatment at all. Okay? So let's talk about medication. If I'm testing a new cholesterol medication and I want to know if this new medication is better than what's already out there, it's kind of unethical for me to make people who need medication have no medication at all. Hey guys, you're not taking any cholesterol medicine. I'm giving you fake pills so you won't know what's going on. That's not right. So instead of testing new pill versus no treatment at all, you could test new pill against treatment that's already used and is already commonplace. So you can test the status quo against new treatment. It doesn't have to be new treatment against nothing at all. An even easier example, let's say I'm testing two kinds of paint and I want to know which one does better and fades less in the rain. I don't have to have a section of pavement with no paint at all before I do my first paint and my second paint. I can just do first versus second. Have to have a comparison. Don't always have to have a group with no treatment at all. And this last part right here, as long as you have these things that I'm talking about, the big ones that we talked about in our lesson here, in your study, your groups should be about identical, and then you can get actually to testing what you want to test. So if you see changes in your variable, in your response variable, then you can begin to talk about whether the explanatory variable actually caused those to happen. Now, it talks at the end here about there being two possibilities and stuff. We'll get to those later on. So there's a little disclaimer for that. But all this bottom part right here is saying is if you do a good job designing your experiments, then you can actually begin to talk about cause and effect, talking about whether the explanatory variable caused the difference you are seeing. So to close things out in this section, I have just really quick here, my little thing moved, but it's just a summary of the 4 big principles of experimental design. So these 4 things that are written right here, make sure you read through these, make sure you understand them. And anytime you're designing your own experiment, these are all things you want to consider.